Okay, I'm going to look at the next steps in probability, which involves questions called conditional probability questions. And we'll start off by looking at an example. Classic Venn diagram probability question. If I've got some students doing archery, some students doing badminton, then I can represent the information on a Venn diagram like this. You're familiar with these. So the number that do both would be 16, the number that do neither, 48. And if I ask you probability questions, you can use the Venn diagram to get the answer. So if I ask you for the probability a student does archery and badminton, then it would be 16 out of the total number of students, which is 100. So 16 out of 100. So we're already familiar with probability questions like this, but we're going to add an extra element to the questions we're going to look at. We're going to put a condition on the question. So consider this. What's the probability that a student does archery given that they do badminton? So this is the condition. I'm only talking about students now that do badminton. So have a think about what that might be for a moment, and then we'll continue with the explanation in a moment or so. The effect of this, given that they do badminton, limits the sample space. So I'm only now looking at these badminton people. So the answer to the probability question is going to be out of 30. I then look at which of those 30 answer the question. So probability a student does archery. So it's just going to be these 16 students out of those 30. And so to write my answer, here's the notation. This bar B, this reads the probability of event A given that B has happened. So the probability they do archery given that they do badminton. I can already see the first thing to figure out for this is that the condition defines the bottom of the fraction. It tells me the sample space. And given they do badminton, it told me that it was going to be out of 30. And then the answer to the question they do archery is these 16. So I've got that answer there. I can cancel that down to 8/15. So there's my answer. And if we think about this a little bit more, then the formula for conditional probability, if I just keep the Venn diagram in view there, I can see that the probability of A, given that B has happened, well, the condition is B, so that the probability that it was event B was on the bottom. And then this number on the top came from the intersection, the ones that were both A and B. So I've got A intersect B on the top. And that's the formula for conditional probability. However, I would only use this if I really have to, because almost all of the questions that you are given that are in context with the Venn diagram, or we'll see in a lesson or so's time with the tree diagram, you can actually answer just from the diagram. So you need to be aware of this, but you'll be able to answer many of the questions without using it, just by applying the logic that we used up here. Look at the new sample space and then answer the question from the new sample space. Okay, there's a few other little things to mention as well. Thinking about independent events. Now, we looked at these with our previous probability work. So I know that if they're independent, we already know that the intersection would be probability of A and B is probability of A times the probability of B. If we now think about in terms of conditional probability, there's an impact here on what these outcomes would be. So the probability of A given that B has happened. Now, again, I'll leave you to just think for a moment about this, but if B has happened and they're independent, what effect does that have on the probability of A? And therefore, what do you think is going to be the result here? Let's follow this thought through. If they're independent, whether B happens isn't going to affect the probability of A happening. So the condition that B has happened here has no impact. So this will be just the probability of A. And similarly here, the probability of B given that A has happened, well, if they're independent, A happening or not has no impact on B. So this would just be the probability of B happening. So again, we've got another way in which we can tell whether events are independent. This can also be used as a test for independence. If you've got events that you know that this is true, then you know that they're going to be independent. So that's a consequence of independence. So you've now got this result for independent events and also this conditional result. Also going to look just very briefly at mutually exclusive events. Now remember, mutually exclusive events are ones that they can't happen at the same time. So here the probability of A and B happening is 0. So let's follow this through. I'll leave you again for a moment to think about what the consequence of that will be. If B has happened, what's the probability then of A happening? If you follow the logic through, A and B happening, they can't both happen. So if B has already happened, A cannot happen. So this has to be 0. And similarly, probability of B given that A has happened, well, if they're mutually exclusive events, then A happening means that B can no longer happen. So again, 0. So these conditional results sort of simplify. If you've got a mutually exclusive event, you know the conditional probability here is 0. And as we saw before, if they're independent, then there's also a consequence for these conditional probability results. We will look at tree diagrams and conditional probability next, but for the moment, I'll leave you to do some practice on these questions.